Hey, AP Physics 1. This is number 2006, number 2 of the AP style type questions for kinematics. We have a world-class runner can complete a 100-meter dash in about 10 seconds. They show that runners in a race of this kind at this caliber accelerate for a time and then run at a constant speed the rest of the race. So this person is visiting your physics class and you need to do a procedure, just develop a procedure that allow you to determine that uniform acceleration and the approximate value of time for that runner in that 100-meter dash. You've got a straight track and you have a whole class of 11 students. So some really important items here. First thing that they want us to do is check the line each of the appropriate items in the list below, select the equipment other than the runner of the track that you need to do the experiment. So one of the things that you have to do the experiment is a stopwatch, so some way to measure time. The only other thing that you need is a meter stick or a tape measure or a ruler. Probably the best thing to use here maybe might be a tape measure, but as long as you have a distance measuring device, you're good. In order to get the points for this one, they're going to give you 1 point for the time, 1 point for the distance measuring equipment. So as long as you have those two things, you get those 2 points. Now we need to outline a procedure, including a label diagram. So the first thing that I would do is show that diagram. So this is our start line. So we're just going to write start. And then we're going to put people 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 people. So we've got each one of our people 3, 4, 5, 6, 7, 8, 9, 10, and they're all 10 meters apart. So what we'll do is we're going to put a little arrow here for our diagram, and we're going to say this is 10 meters. And then you'd want to go through and just show that these are all 10 meters also. You could maybe write down 10 meters, and then you could show that for each one of these if you wanted to. 10-meter distance, totally up to you, however you want to do that, but you got to show that that's what that is. So if this is a start, here's 10 of your people, and then you have one more person on the start line, and that person is just to get everybody going here. That's 1 point. So as long as you have your diagram, you end up with 1 point there. The next thing you need is distance measurements for 8 to 11 fixed positions. So you need to make sure that you have distance measurements. So I'm just going to put distance measurements. Distance measure for 8 to 10 fixed positions. So here I've got people at every 10 meters. So this would be 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So I've done that for all 10 of my positions. So as long as I do that, I end up with a point. The next thing that I need here is to make sure I have time measure for 8 to 10 fixed positions. So we need both of those in order to figure out kind of what's going on here and get our acceleration. The next thing that you're going to need to do is you will have to have an experimental technique. So you'll need to say the runner will start on the start line. The first person will yell 3, 2, 1, go, and then each person will start their stopwatch on go, and then stop the stopwatch when the person gets to their position. And then that way we've got 10 different times for 10 different positions. So actually telling about the experimental, so I'm just going to write down what they're looking for, experimental procedure. Doesn't have to be long, but it needs to give what you're going to do. So there's another point. We already said the diagram is a point. And then the last thing that they want us to do is make sure that we take data. So we're going to take data in a single run. So you're not going to have the runner turn around, come back and do it again to 2, and then turn around and go back to 3. We want to do it all the way across. So go ahead and take all that data in one fell swoop. We'll just say it's really cold outside, and that's what needs to happen. The next part of this problem that they want us to attack here is it says outline a process of data analysis, including how you identify the portion of the race that is uniform acceleration and how you would calculate that uniform acceleration. So here you either need to have equations, okay? So you either need to have equations or you'll need to write out um, how to write out how you're going to find those two areas in question. So we'll have to use equations, or we're going to write out how we're going to identify that portion where we have uniform acceleration. So one of the things you might say here is you're going to plot all the points on a position versus time graph. And then where you plot and it's a upward sloping curve, we know that that would be our uniform acceleration. So here we would say this is uniform acceleration, and then where it is a straight line for position versus time, that would be your velocity. The other thing you could do is you could use equations. So we know we have several equations we can think about. We could say that the distance, okay, so the delta x, that's the same thing, distance or delta x is equal to the original speed times time, which we know is 0, plus 1/2 at squared. So you could talk about this equation and how that might help you determine what the acceleration is. We know the distance. We know that this is 0, so now you just have to plug in your time and 1/2 of your acceleration, so you can kind of figure that out. But I think the best way to do this is to actually use our graph here. Um, so the next thing that we have to do is make sure we clearly, so here we're going to clearly and accurately identify, so we can identify the unknown time, TU. Same thing, clearly and accurately identify the unknown acceleration. And you don't want to make any incorrect statements, so don't go on and on and on, because they will actually take points off if you say anything wrong. So no incorrect statements. The rest of the 3 points that you get is just for making sure that you have a very clear and coherent paragraph that answers all those questions. So this is 1 point, 2, 3, this is 4, and then there are 3 more points for showing that. So what I'm going to do now is I'm going to show you what an answer might look like for this one, so you can actually see what a good answer would be. So I've brought up an answer, and you can see that it's got everything in it that we need. One of the things that it has is it shows this 10-meter interval. It shows the times that we're taking. It shows where all the people are. It shows the runner, and it shows me. So those are the things that we need to show. And then it goes through and talks about what's happening. It says use the tape measure and chalk to mark off the 100 meters in 10-meter leagues. Set a classmate with a stopwatch at marks shown. Use a starter's pistol to signal the runner and to run, and the classmates to start the stopwatches. Each person turns off the stopwatch when a runner reaches his or her mark. You then have measurements for each one of those. So that is actually for letter B. So that shows you what a good response for letter B would be. The next part is letter C, and I can kind of show you what that would look like here. We've got a little bit of the answer here. We already talked about these things, so that's the one approach. Here's another approach that you could use. You clearly indicate which variable was used. So if you're doing just the approach using equations, this is what you would do. For description or diagram, that clearly defines all the variables, showing how you use those variables, put that into an equation, correctly solve. But we talked about really just doing this in a graph. So I think that's the way to do it. Just trying to go through and show what's happening in the graph and where all those different parts are. So remember, we said this would be position, this would be time. We could identify AU here by just showing that part of the graph where it's curved. You could circle it, point to it, say that that's AU. And that's really it. I think that's all you need in order to show kind of what's going on. And that is the end of this very large problem.